Hello and welcome to another video lesson with Lawson. Today we're going to be studying our AP Physics C, an introduction to the calculus that you'll need to know, important concepts related to differential calculus and being able to describe some of the derivatives and foundational rules that you'll need to apply throughout the course. To define the derivative, there's two different ways we're going to look at this. We're going to start with the more math-based content, which is looking at it in terms of it being a limit as we take 2 points along a line or a curve and we bring them closer to each other. So what we're really saying is that if we have a function or some output that you get for some input, in this case we're talking about an output of y or an output of f of x and an input of x, then as long as there's a limit that's defined that describes a function that's differentiable at x. We could also describe that in terms of finding it a certain value. So we can find the derivative function, which describes it everywhere along the curve, but we could be looking at a specific input, a specific value. In this case, we note that as a derivative at a point A, or if we're looking for the slope of the line or the tangent at point A, we can take that derivative function and input the value a to be able to find out what the derivative is or what the slope is at that point. Looking at this curve, we're going to take 2 points noted here as the green dots and separate them by the distance. We could call that h. And then we're going to gradually bring that second point closer to the original point by making h smaller and smaller. And eventually h will be so infinitesimally small that we'll be able to essentially get the slope of that point. The truth is you can't get the slope of a point. However, we can get the tangent line at that point. And it turns out the tangent line at that point, since it's a line and it has a slope, we treat them as the same thing. So the slope of the line or the tangent line for a curve is what the derivative really is or what it represents, how much that output is changing relative to the input. So we have some input variable, in this case shown as x. We have some output variable, which we were saying either y or f of x. And in those two relationships, what we're really looking at is how you change the input changes the rate at which the output is changing. So we're not looking at the output itself, we're looking at the rate at which the output is changing. Right now, we're sticking to some of the classic math terms. But in this class, we're going to be using a lot of variables other than x and other than y. So we're going to start introducing that pretty soon as well. How we'll represent our derivatives. The most common example is to show the variable with the prime, the little apostrophe above it, f prime, or we might say the derivative of the function, capital D of f. What we're really saying is that if there's some value or some y is equal to the output, the f of x for some input, in this case x being the input, then we can find the derivative of the output relative or in terms of the input. If we had the output y and the input x, we could find the derivative of y in terms of x. Or we could find the rate at which y is changing as we input x. You see several different ways that this is denoted below. The most common one, or the one that we'll see most often in this course, is the derivative of the output variable divided by the derivative of the input variable, or essentially saying that we're going to find the output variable, how it changes in terms of an input variable. X will be one of our output variables, not one of our input variables. So we might be describing x in terms of t, or x in terms of v, or x in terms of a, or x in terms of a different variable. In that case, it would be the derivative of x relative to t, or relative to a, or relative to the other variable we're describing it, or the variable that we put in as an input. We'll also, in addition to being able to look at the derivative functions or being able to determine the derivative functions, be looking for what the derivative is at a specific point, saying how it's changing at a specific time, how it's changing at a specific position. And in that case, what we'll be doing is, instead of doing it in terms of that input variable, t or x or v or a or whatever the input variable is, we'll actually be looking at it in terms of a value at the checkpoint below where it talks about finding the derivative at a specific point a. Those are some of the ways we denote or notate what the derivative is at a specific value. You want to be familiar with all of these different ways of representing it for both this class and your math classes. But we're really going to focus on just a couple of them that will be used mostly through this course. But you've got to be as math literate as you can be when you're working with derivatives. Again, right now we've stuck to the x and y variables, but very quickly we're going to start, especially in the example problems I'll do in a couple moments, start using variables other than x and y, although they might be included as well. we're going to go over some of the very important rules, or some of the things that you'll want to memorize in terms of applying derivatives or applying differential calculus. You'll find that most of the rules you need to know for this course are relatively straightforward, challenging and requiring effort, but in terms of calculus content, much more straightforward and much more easy to apply than some of the other theories or some of the other applications. Let's start by looking at the derivative of a constant. Since a constant is a horizontal line, that means that the derivative, or the rate at which the output changes, since it doesn't change, is 0. So the slope of a constant is 0, therefore the derivative of a output relative to a constant based on a constant input is going to be 0. That's going to come in handy when we're trying to apply some of these rules. When we're applying the derivative of a variable, when we're defining the output based on input, where the output is equal to the input, f of x equals x in this case, or y equals x in this case, what we see is a line that has an exact 45 degrees, or that it has a slope of 1. So the rate at which x and y change is equal. The derivative of y in terms of x, or derivative of f of x when that is equal to x, is 1. In some ways that's similar and actually kind of an application of the power rule that's right below, but it's just a shortcut and it makes it a little bit easier to apply when we're doing some more complicated math with it. When we have a variable to a power, where the power is a constant, in this case represented as n, but n is some constant, we could multiply n by the original variable to the power of n minus 1. So what we do is we take that exponent, we drop it down and put it in front of the variable, and then we use the variable to the exponent minus 1, and that's how we apply the power rule. You'll notice in the power rule there's an asterisk next to it. That's because this rule is described on the reference table. There are several calculus rules that are described on the reference table, but you need to memorize and be able to apply these without having to refer back to the reference table. If you're finding yourself searching through the reference table to be able to apply or to be able to understand how to apply these, you're going to find this course is very challenging, and a lot of the problems will very quickly get very thick and very difficult for you to be able to maintain and work through. Make sure you work on memorizing and understanding each of these rules and being able to apply them. Let's look at a couple of examples. Starting with the constant. Let's say that we have a constant where it's f of x is equal to 3. Now in that case, what we're trying to do is we're finding out what the derivative of the output is relative to that input, or d of y over d of x, or f prime of x. And what we see is that those are equal to 0 because 3 is a constant. Let's apply the variable rule using a variable other than x or y. Let's have the function of t being equal to t. In that case, we're finding the derivative of the output, y, in terms of t. And in this case, f prime of t is going to end up equaling 1, because t is simply a variable, some input. Let's look at the function of v equaling v to the 5th. The derivative of the output in terms of the input v, or the first derivative of v, end up equaling the exponent times the original variable to the exponent minus 1. Right now I'm showing all the steps, but very quickly we should be able to subtract 1 without issue to any of these exponents. And so what we really find out is that applying the power rule, we find that this is 5v to the 4th based on the original function. Let's look at some other rules, and we're going to get gradually more complicated as we're going through it. It's important that you're comfortable working with natural logs, both in the form of e to an exponent and the natural logarithm itself. Natural logarithm is relatively straightforward. The derivative of the natural log of x is 1 over x, and again we can use a different variable other than x, but the same pattern applies. The derivative of e to the x equaling e to the x, regardless of what variable you substitute in for x, is the only function we'll use this year where you get the exact same function out as the derivative that you had as the initial or original function. When we look at the trigonometry rules, there's a lot of them that are available and a lot of them that you might need to know for your calculus courses. There's only a couple of them that will really come up in this class. It's important to know the derivative of sine and the derivative of cosine and how to apply them. In the second examples of the sine and cosine, you'll see that you could actually describe that another way later on using the chain rule or the composite rule, the function within a function rule. However, you can also just memorize how to apply these constants. Either way, you'll be able to get to an answer relatively quickly. The derivative of sine of x is cosine of x. Sine's derivative is cosine. The derivative of cosine of x is negative sine of x. So the derivative of cosine is negative sine. In this case, we're applying x, although you'll see when I do the examples, we're going to use a different variable, much more common to when we're describing things that we might be taking sine or cosine of. When we have a constant, when that variable x is being multiplied by a constant, we can still take the derivative of it. So the derivative of sine of x is cosine of x. The derivative of sine of a constant times x is that constant times the cosine of that constant times x, as you see shown here. While the derivative of cosine of constant times x is that constant times negative sine of the constant times x. Let's say that we have a function f of v that is equal to the natural log of v. In this case, if we want to find the derivative based on that input v, or f prime of v, that is simply 1 over v. Imagine we have a function L of I is equal to e to the I. The derivative of that function, or L prime of I, is equal to e to the I. Applying the trigonometry rules, we're going to use something other than x, which is much more common. In this case, we're going to look at theta. Let's say that we have x of theta is equal to sine of theta. Then the derivative in terms of theta as our input, or x prime of theta, is going to equal cosine of theta. We can do something similar when we're looking at multiplying it by a constant. We'll say that y of theta is equal to sine of 4 times theta. The derivative in terms of that input, or y prime of theta, is going to equal that constant 4 times the cosine of 4 theta. Looking at the cosine examples, let's say that a of phi is equal to cosine of phi. Then the derivative based on that input phi, or a prime of phi, is going to equal negative sine of phi. And looking at another, multiplying it by a constant, let's use v of phi is equal to cosine of 7 times phi. The derivative based on that input phi or v prime of phi, is going to equal negative of that constant, 7, times the cosine of 7 phi. Initially, since it's the beginning and we're seeing a lot of different variables, I imagine there could be a little bit of confusion as you're looking at this, which is perfectly fine. But you've got to get very comfortable working with any variable that can be given to you in a mathematical way. It turns out that right now we're looking at a lot of the math theory. And what I like about physics is that it's really about applying the theory and physical descriptions. These will actually relate to physical parts of our universe. We'll actually be looking at things in the universe that exist, variables that we use to represent those physicalities, those parts of our universe in that function. It's very important that you're comfortable seeing things other than x's and y's and working with them with just as much care and with just as much skill. Finally, we're going to look at some of the rules that come into play when we have multiple things going on. In the first instance, we're going to look at multiplying a function by a constant. So either we're multiplying the function itself by a constant, or we might see a constant that we can factor out of the function. In either of those cases, we can apply the constant product rule, which is that the constant times that function is equal to that same constant times the derivative of that function, as well as the function product rule. Function product rule is if we see two functions that are being multiplied by each other. In that case, we can take the first function and multiply it by the derivative of the second function and add to it the derivative of the first function times the second function. It's kind of an interesting situation there. We don't multiply the derivatives. We multiply the function by the derivative of the other function and then switch it and add them together. The sum or difference rule is when you're adding or subtracting. You don't do either adding or subtracting. When you're adding, you take the derivative of each function and add them together. When you're subtracting, you take the derivative of each function and find their difference. And finally, we'll look at the composite rule, or the function within a function rule, or sometimes referred to as the chain rule. In the chain rule, what we see is a function within a function. We'll usually use a u to represent that internal function. So what we're really saying is that if we have a function within a function, we can set that internal function equal to u, or substitute u as an internal function, find the derivative in terms of u, and then find the derivative of what u is equal to, and then multiply those two by each other. So what we find out is the derivative of the external function and the derivative of the internal function, and the product of those derivatives will end up giving us the derivative when we have a function within a function. Let's look at a couple of examples. Imagine that we have a function x of t, and that is equal to 6t cubed. What we see here is that constant 6 times a function t cubed. What we're going to actually do when we're looking at the derivative in terms of that input, or x prime of t, it's going to equal that constant times the derivative of t to the third power. That's the power rule. That's 3 times t to the 3 minus 1, or t squared. And 6 times 3 times t squared is equal to 18t squared. Next, let's apply the product rule. Let's say that we have a function v of x that is equal to 8x times x to the fourth. What we see is we're multiplying two functions, one function 8x and the other function x to the fourth. So we take the first function and we want to find the derivative based on that input, or v prime of x. So we take the first function, in this case 8x, multiply it by the derivative of the second function, that's the power rule, 4 times x cubed. Then we're going to add to that the derivative of the first function. That's a constant, 8 times a variable, x. The derivative of a variable is 1. So 8 times 1 is 8 times x to the fourth. This is 8 times 4, or 32x to the fourth. 8 times x to the fourth is 8x to the fourth. 32x to the fourth plus 8x to the fourth is how we find out that this derivative is 40x to the fourth. Let's make some room. Instead of doing both a sum and a difference, we're simply going to do a difference. Let's say that we have a function a of t, and that is equal to 3t squared minus t squared divided by 4. While it's true we could combine terms, instead let's treat it and leave it as a difference. To find this, we're going to take the derivative of each function by itself and then subtract them. The derivative in terms of the input t is going to be constant times the power. So that's 3 times 2, which is 6t, minus a constant 1/4 times 2 times t. 1/4 of 2 is 1/2. So we see that this is equal to 6t minus t divided by 2. We can either leave that 5.5t, or we can write that as 11/2 t. Finally, let's look at the composite or the chain rule. F of x, that's equal to the natural log of 2x to the 9th. In this case, we see the function within the function. The external function is the natural log, while the internal function is 2x to the 9th. The derivative relative to that input of x, what we're actually going to do is say, well, let's let u equal 2x to the 9th. And then we're going to find the derivative based on that input u, and then the derivative of u based on that input x. And that will end up getting the derivative of that original function. When we're doing that, we're going to take the original function, which is natural log of u. Natural log of u is not too hard, because natural log of u ends up equaling 1/u. And then we're going to find the derivative of u in terms of x, and this is 2x to the 9th, that's a constant, times a power. So that's going to be 2 times 9, which is 18x to the 8th. u is equal to 2x to the 9th. This is actually equal to 1/2x to the 9th times 18x to the 8th. 18 divided by 2 is 9. X to the 8th divided by x to the 9 is x to the 8 minus 9, which is why this is 9x to the -1, or 9/x.